Planets Laboratory's Neighborhood Lecture Series. To participate in tonight's live Q&A, please visit the URL on the screen at pigeonhole.at/volcano. That's pigeonhole.at/volcano, or simply scan the QR code. There, you can submit your questions, view others, and even vote on your favorites. Thank you for joining us. The program will begin shortly.
Right.
Welcome to the Carnegie Science Earth and Planets Laboratory Neighborhood Lecture Series. To participate in tonight's live Q&A, please visit the URL on the screen at pigeonhole.at/volcano, or scan the QR code. There, you can submit your questions and vote on your favorites. Thank you for joining us. The program will begin shortly.
Hey, good evening, everyone. How are you all this evening? Beautiful night. Yeah. I'm Mike Walter, and I'm the director of the Earth and Planets Laboratory here at Carnegie Science. And it's my great pleasure to welcome you here this evening and to introduce tonight's speaker, Dr. Diana Roman. Diana studies volcanoes, and she's been doing that for several decades now. This sort of Jules Vernean journey started at the University of Oregon, where she received her PhD in 2004. This is one of the premier volcanology departments in the world, really. After that, Diana won a prestigious National Environment Research Council fellowship in the UK, where she spent several years at the University of Leeds. She was then offered a job at the University of South Florida, where she became a faculty member. And I think she spent about 5 years there. And in 2011, we were lucky enough to attract her, and she accepted a position as a staff scientist at the Department of Terrestrial Magnetism here at Carnegie Science. Diana's research is really into understanding the way the guts of volcanoes work. So a lot of volcanologists study the lavas and the gases that come out the top, and that's really important information about where the magmas come from, how long they might have been beneath the volcano, lots of information, maybe residence times. But you can't really see the complex dynamic workings of the magma system. You can't really understand how the magma is moving around, what causes it to move, and what causes eruptions. A lot of that has to do with the interplay of the magma, which is very fluid, and the volcanic carapace, which is brittle, and there's lots of faults, and those faults break, and they sometimes lead to eruptions. So Diana's approach really straddles volcanology and seismology. So when those earthquakes happen beneath the volcano, they send acoustic waves up, and Diana can put seismometers on the surface of those volcanoes, like this one here. This is called a quick deploy box. This was something Diana will tell you about, developed here at Carnegie. So Diana can go off and deploy these on active volcanoes, get the earthquakes or measure the earthquakes, and understand something about the dynamics of magma movement and storage beneath the volcanoes. Diana does this all over the world. Where there's an active volcano, that's a place that you might find Diana putting one of these quick deploy boxes. So she spent a lot of time in the Western US studying the Cascades, in Central America, places like Guatemala, wherever there's active volcanoes, South America, in Chile. We'll hear tonight about her work in Alaska. She's put volcanoes in Italy, Africa. I'm probably missing a few, right? Diana's a real explorer, and you'll get to hear about some of that tonight. So tonight, I should also mention that in 2021, so we became the Earth and Planets Laboratory in 2020, 2021. And Diana was made the H.O. Wood Chair of Seismology at the Earth and Planets Laboratory. And tonight, Diana's going to tell us about a hidden supervolcano in the Alaskan Aleutians. So Diana, take it away.
Thank you much. Thank you all for coming on this beautiful evening. I want to tell you this particular story, not just because it's really exciting and it's still evolving, and it's actually very controversial, but also because I think it really encapsulates some of the key facets of how we currently, as volcanologists, do our research. First off, volcanology is incredibly interdisciplinary. So as you heard from Mike, I'm a seismologist, but I've listed I think I've listed all of the team that's worked on this project so far. You can see it's a long list and it's growing every year. This project involves geochemists, geologists, geochronologists, structural geologists, and on and on. And so I want to acknowledge my colleagues, some of whom have gone through heroic efforts for this project, and their half dozen institutions, because this is really, we can't, I can learn the seismic story, but it only starts to make sense, as you'll see in this talk, when we bring in information from the rocks, from how the ground is deforming, from how gases are coming out of the volcano. So volcanology is very interdisciplinary. Volcanology is also really a discovery field, a field of exploration and discovery. So we can't tell the volcanoes what to do and then do an experiment. We can't follow the scientific method and say, okay, you two turn on, but do this a little differently. We really have to react to what the Earth gives us. And often, because of that, we find that when we go out to study a volcano for one reason, we find something completely novel and different. And that's very much the case here. We did not go to the islands of the Four Mountains thinking that there was a large caldera system there. And we're also extremely data limited. So many of these volcanoes are in remote places, and many of them are underwater. And it's very, very difficult for us to get instruments to run out in these environments through long winters and hot summers in corrosive, gassy environments. So we're always being very creative with how we can get information about the systems, and I'll show you some examples of that. Okay, so I'm going to start with my punchline. My punchline, and what I'm hoping to convince you of in this talk, is that we have discovered a 166,000-year-old caldera in the islands of the Four Mountains, and we think this is the largest volcanic system, the largest caldera in Alaska. So you'll hear me say IFM. IFM refers to the Islands of the Four Mountains group. It's this beautiful ring-like set of islands. I'll be talking a lot about Cleveland, which is the active volcano, and Cagamil in particular in this talk. We think that the caldera system, we initially thought that the ring of islands outlined it. We've adjusted that a little bit, as you'll see. So we think that this is something like 20 by 25 kilometers across. And just to put that in reference to some of the other large caldera systems, Fisher is the largest at 10 by 17 kilometers. And so this one is larger and possibly much larger. Where is IFM located? It's very, very remote. So here you can see the Aleutian chain of volcanoes. All of these little islands are volcanic, at least up to a point somewhere around here. There's Anchorage for reference. There are very few people living out here, so it's quite remote. And IFM is sort of right in the middle of the chain. So I'll tell you a little bit about how and why we care and how we work there. It's quite an adventure. But before I do that, I want to admit that a little trick that I played with the title of this talk. And some of you may have noticed that the term supervolcano is in quotes. So it's a bit clickbait. It got you here, but, and now you're all gonna leave. Volcanologists really don't like the term supervolcano. And I'll refer in particular to this nice commentary, why I dislike the term supervolcano, which was written by the current scientist in charge and a good friend of mine, Mike Poland. He's basically in charge of the monitoring agency that watches Yellowstone. And the reason we don't like supervolcano is because it's a little overused, but it also implies that that volcano is only going to have large eruptions. So it links the size of the eruption, super eruption, to the size of the volcano or to a specific system. And in fact, Yellowstone mostly has small eruptions. And we expect that if and when Yellowstone erupts again, it's most likely going to be a very small eruption. Sure, it's had several super eruptions in its history, but we'd rather talk about super eruption than supervolcano. And really the term that we use for these large systems, which I'll explain in a moment, is caldera. So I'm going to switch from supervolcano to caldera. I also want to point out some of the press coverage that we got on this story when we first presented it a few years ago at the American Geophysical Union meeting. It got a lot of press. Nat Geo managed to keep the term supervolcano out of its title. Thank you, Maya Haas. But clearly you can see here that a lot of our coverage was this back and forth of we found Alaska's Yellowstone. We found a supervolcano and a rebuttal by a great volcanologist and sort of popular scientist explaining why we haven't. And really his point was actually that it's a caldera maybe, but it's much smaller also. So Yellowstone, I told you, we think IFM is 20 by 25 kilometers. Yellowstone is about 100 by 80 kilometers wide. So it's an order of magnitude bigger. So we're not talking about Yellowstone here, even if we are talking about the biggest volcanic system, the biggest caldera in the Aleutians. Okay, so what is a caldera? And this leads into like the evidence. It seemed simple. I'd actually avoided calderas for most of my career before I got sucked into this, this fascinating project. It's a wide topographic depression. So topography just meaning the shape of the earth, or I'll say bathymetry, and that's just topography underwater, formed by subvertical subsidence into a partly drained magma reservoir, typically during a large eruption. So it's both a feature, but also a process. So basically we have an eruption that empties out and creates this big hole, and the roof caves in, leaving us with something like what we see at Crater Lake, Oregon. So this is a very famous and beautiful caldera. It's got a resurgent dome here in the center. So you would think that it would be pretty easy to say, is it or isn't it a caldera? And I learned it's not. I'll come back to some of these features when I start to go through the evidence, and I'll explain them to you. Okay, but first off, why do you care? So it's not a supervolcano, and it's really remote, and it's pretty old. Why should we care? Well, first off, even at remote volcanoes, like in the Aleutian, volcanoes, eruptions of this magnitude can actually have global impacts. And just as a case in point, this was a fascinating study that came out in Proceedings of the National Academy a few years ago, linking the 43 BCE caldera-forming eruption of a volcano called Okmok, which is right next door to IFM, to the onset of the fall of the Roman Republic and the Ptolemaic Kingdom. So a combination of climate effects leading to political instability, food shortages, et cetera, were tied ultimately back to this very remote Aleutian volcanic eruption. Okay, so I told you 166,000 years. We don't think there was a human settlement in North America then. So we should still care, because calderas, eruptions of this size, have impacts on our climate and have impacts on evolution, on the history of fauna and flora. And it's really important for us to understand these, particularly in the time of climate change that we're now going through. So just as a really interesting illustration, this figure on these are complicated, so I'll just tell you to take away. So what we've got here, these blue squares are very abrupt cooling events that are thought to be linked, some are actually associated with volcanic ash, that are thought to be linked to large volcanic eruptions. And up here, we've got their culprits, the whodunit. And what I want you to see is that most of these, still the eruption itself, the volcano, hasn't been identified. Okay, so here's Toba, right? That's a big one. And we've got that one, but we're missing. We know that there were many more large eruptions in our planet's history than we've actually been able to go out and identify the volcano that did it. In fact, just a few years ago, a major climactic event in 1527 was finally linked to an eruption at a volcano called Rinjani in Indonesia. So we're still looking for these to understand why our climate has changed. There are also clues that large volcanic eruptions in the northern latitudes, including Alaska, have had major effects on the faunal record. So the megafaunal extinction was something that happened very quickly and somewhat puzzlingly quickly. And one thought is that it was driven by large eruptions in the northern latitudes, including Alaska. Okay, so another point before I move on about climate, because this is gonna come back as my mic drop at the end. Another interesting thing, so we're missing eruptions here, but we also have a record in the geologic record. We can find ash beds, and in the Aleutians in particular, we find a lot of these ash beds in the Yukon, in interior Alaska, and most of them we have not tied back to which volcano did it, but also the known calderas in the Aleutians, we haven't found their deposit on land. So there's really something missing here. And in particular, a famous one is called the Old Crow Tephra. It's a very extensive ash deposit throughout the Yukon and Alaska, where its source is unknown, and its source has been very controversial. We can't find, this was a huge eruption. We cannot figure out which volcano did it. So I want you to remember Old Crow. I'm going to come back to this, okay? This is a bit of a spoiler. And then we care, of course, because we want to know about the hazard, right? Eruptions are hazardous. So Cleveland, which I had mentioned on the earlier slide, is the active volcano in the islands of the Four Mountains. It's actually the most frequently active volcano in North America. And you can just see on this little plot here. So I've done a little timeline here for all of the volcanoes in Alaska. And you can see how frequently it erupts compared to the other ones. So it's like low-level eruptions, but it's different than its neighbor. It's also different because it's this little cluster of islands as opposed to like one big edifice. So there's something there. But also we care about Cleveland and we care about the system because there is a big threat from these very remote volcanoes to aviation. So raise your hand, how many of you have ever taken a flight from anywhere on the Eastern Seaboard, DC, New York, to anywhere in Asia, Tokyo, Beijing? Yeah, I see a lot of hands. Okay, when you're taking that flight, this is the route you're taking, okay? This is the fastest way. You go way north and you fly over all of these volcanoes, okay? All the volcanoes of the Aleutians, Kamchatka, and the Kurils. So jet aircraft don't play very nice with volcanic ash, which is actually glass. It can melt and gum up the jet engines. So don't worry. Every time I do this, I'm like, wait, somebody's probably getting on a plane next week. To reassure you, we have a really good system in place to avoid ash aircraft encounters, but it is a reason that we care about these eruptions at these remote volcanoes. Okay, so I told you that I didn't go out to the islands of the Four Mountains to find a giant caldera. I actually went to Cleveland for the first time in 2015 as part of an NSF-funded study that was really aimed at something very technical. We had a very technical hypothesis about how this group of volcanoes, so there's Cleveland and IFM, there's Okmok, the Roman Republic killer, how this group of volcanoes might respond to their tectonic setting. And so we basically went to Cleveland because we thought it was an end member in its behavior. And so we went out there to put out some instruments and to collect some samples. I'm going to come back later in the talk to talk a little more about life in the Aleutians in the field, but just as a shout out, if anybody wants the Puffin incident story, ask me later on in the Q&A. So we went out and basically what we ended up doing was Cleveland was one data point in this really nice study that we published last year in Science. It turns out it's not the end member we hypothesized, but I'm not going to talk about this study. But the point is that as we were wrapping this project up and this study up, we started to kind of talk about some of the strange things that we had started to see in the data that we'd collected. And it almost seems obvious in hindsight that it took us this long, but we started to speculate that the IFM was actually the site of a very large, look, there's a ring right there, a really big volcanic caldera. And of course, then the question is, well, is it? I told you it's controversial. We may be wrong. People have looked at rings of volcanoes and suggested they were calderas, most famously in the Sisters in Oregon, if any of you are familiar with the Oregon Cascades. So is there evidence that it is? And if so, how big really is it? How old is it? Where is the rim of the caldera? Is it still potentially active? Is there still a large magma reservoir that might make it capable of large eruptions? Okay, so then notice the date, May 2020 was when we started talking about this, early pandemic. And we started to kind of chew on this and say, okay, well, what should we be looking for? First of all, coming back to this kind of textbook diagram, okay, first thing first, is there a big hole? We should be able to see that, and that should tell us, where it is and how big is it? And is it made up of multiple little holes or just one big hole suggesting it was one big eruption? And this is all underwater, right? So, of course. Our tool there, as you'll see in a slide or two, is basically seafloor bathymetry. So bathymetry, just the surface of the seafloor. And then another big feature, if there was a big eruption, is that we should find the deposit of that eruption. So we should be looking for a very large, thick ash sheet. We often refer to this as an ignimbrite. I'm going to talk about it as an ash sheet, but if I slip and say ignimbrite, that's what I mean. We might also see that there's kind of a post-caldera, maybe uplift and some lava flows as the last bit of magma kind of slowly bled out. So we might be looking for something like that. And often when we see these ash sheets, because they're so thick, they basically insulate themselves and they bake themselves. So they weld, and we find them not as loose ash, but we actually find that they've kind of glued together because they were able to stay hot into what we call the welded ash sheet. So for that, we're looking at field geology for how old. We want to see if we can find some deposits and then figure out their age. So these are the types of things that we're after. And then for is it potentially active, we're going to want to look at things like seismic tomography, which is basically like a medical CAT scan of the Earth's crust. Or we might expect if there's a lot of residual magma, magma is going to be less dense than the rock around it. So we might actually see that the gravity around the area is slightly lower than it is farther away. So we did a really creative, my colleague Helen Lemaville did a really creative thing here. And then also for activity, are there are there recent eruptions throughout? We know Cleveland is active, but what about the other volcanoes? We might see evidence that they've erupted recently, that they are actively degassing, that they are hot. So these are all things that we will be looking at to see if we can assess whether there's still this large residual magma reservoir. Okay, so there we go. That's the plan, right? But we're in a pandemic. And we had a lot of time. So we got really creative. The first phase of addressing this problem was mostly done using a combination of data that we could get off various satellites, in particular for the gravity work, and also some very interesting legacy bathymetry data from the post-World War II era, when NOAA actually went out through the Aleutians and figured out a lot of the bathymetry. And so we were able to kind of pull up this old data. But that we couldn't get out to the field. This was what we had, and we were itching to kind of test this idea. Okay, so here we go, the evidence, the smoking guns. So first off, is this the site of the large volcanic caldera? Where is it? How big is it? So we're going to look at bathymetry. So on the left-hand side here, we took these 1940s era bathymetric soundings that were compiled by NOAA, and we digitized them, and we built this really nice bathymetric map. And what you can see is that here's our ring of islands. So this is Cleveland here. We do see structure that looks like it might be the rim of an old caldera, but it's offset from that ring. So at that point, our thinking actually started to shift the caldera a little bit to the east, still about the same size, 20 to 25 kilometers, but not centered on the ring as we had originally thought, or at least as far as we can tell from these data. So maybe it actually extends out a little farther. We don't know. There's not as much data out here. And actually more recently, we've been doing a fun thing where we've been crowdsourcing additional bathymetric data depth soundings from some of the commercial crab fishing vessels that work out in this area. So these are the guys that you see out in Deadliest Catch. And they do bathymetry because that helps them figure out where the fish and the crabs are hiding. And they're not happy to share that data with the other fishermen, but they were actually really happy to share that with us. And so it's kind of patchy, you know, they're looking in different areas, but we're right now working on integrating this and some additional data that we've gotten since into this to see if we can get a little more detail. So that was kind of a fun crowdsourcing exercise. Okay, is it potentially active? So early on in this, when we were all in lockdown, my colleague Helen Lemaville, who's a geodesist here in EPL, had this really great idea to use satellite gravity. So satellite gravity is an odd concept, but it basically only works underwater. It works by looking at the height of the ocean surface, the actual liquid surface, and very subtle deviations in the shape of the ocean surface. And when she reprocessed the data from the satellites, she found this gravity low centered a little to the east of the center of the ring. Okay, so that's what we'd be looking for. And it's about the right scale. You can't see the numbers, but it looks like what we see in gravity anomalies at other large calderas. And then she did some nice modeling to show that, okay, one possibility, maybe it's just sediment, some loose stuff that's on the surface, but actually that does not fit this gravity profile. It really does look like it has to be something in the mid crust, okay? So that was intriguing because that suggested that there might still be something down at depth over a pretty large volume that had characteristics of a partially molten volume of rock. So potentially that residual magma chamber. Around that time, we very fortuitously started talking with a group of archaeologists who had been working in the IFM, and we sort of told them this crazy story, and they said, oh, that's interesting, because when we were out there around the same time that we were out there in 2015, they came across some interesting deposits on one of the oldest islands in the Islands of the Four Mountains. So again, this is Cleveland, this is the active volcano, and the ring is kind of up here. And they shared their samples and field photos with us, and it's a welded ash sheet. So there it is. We were stunned, and it's beautiful. It has these textures of larger clasts that were probably plastic enough in depositing that they squished down. We call them fiamme, so flame in Italian. And this was incredible to us. And so, of course, we did what every good geologist does, which was run to our nearest geochronologist and say, can you please tell us how old it is? And we got a date back, and that date was 166,000 years. So that's our kind of, at the moment, our age date for this. And again, these types of deposits can only happen very close to the source, to the active vent. As the ash gets farther away, it cools and it can't do this sort of welding, this gluing together. So we think this deposit was sourced somewhere very, very close to Tana. So that was really exciting. And then we did its chemistry. So this is a really complicated plot. We wanted to see, okay, well, maybe it's something that came from Okmok or from Yanaska, the other volcanoes over. And so what we do in working with these deposits and trying to tie together, the deposit and its source volcano, is we look at its chemical fingerprint. It's basically like a fingerprint. Each volcano has a unique, and each eruption actually has a very unique chemistry. So generally, when we find an ash deposit, we can tie it to other deposits of the same eruption, or we can tie it to the source vent by looking at this fingerprint. So basically what we're looking at here are the red circles. That's our ignimbrite, or our welded ash sheet from Tana. And we couldn't really find a match in any of the known kind of ash record. But what we could say is, well, it doesn't look like any of the other big caldera systems chemically. And we found a few tephras that were kind of in the ballpark chemically. So you can see the Dominion Creek, which is too young, it's not really quite, blue-red overlap. And then here's our Old Crow in yellow, and yeah, it's separating. So it's kind of close to the Old Crow, but it really wasn't compelling. So we couldn't really match it to anything that we found yet in the known record of ash. Okay, so that was as far as we were able to get in the pandemic. And of course, you can imagine that I was itching to get back. We all were. And so, yeah, and maybe not so excited in hindsight. Through really generous support internally from Carnegie, a group of us were able to basically stow away on an expedition back to the IFM in 2022 that was funded by the Moore Foundation, a project called AVERT that's led by Terry Plank and others at Lamont Doherty, basically a technology development project, and they were using the IFM as their really harsh lab to test some of these systems. But we were able to stow away and kind of do our work and share the boat and the field time. And I'll just talk a little bit. The next few slides are going to be, life in the field and what an adventure this was. So in this case, we were working off a vessel called the RV Steadfast, amazing crew. It is basically a floating helipad. It is small, and it is only as big as it needs to be to let this helicopter land and take off from it, which is, next level helicopter flying. Shout out to our pilot, Jordan, here. And you can see here, like, at night, the helicopter would come live on the boat, and if it was choppy or windy, we'd be strapping the helicopter down to the deck. It was intense. And this is we're all alone, living on this boat for 3 weeks by ourselves, no civilization. And so we do a lot of field safety. Here's us in our Gumby suits. This is the overboard drill. If we have to abandon ship, we do helicopter training, we do first aid, wilderness first aid, and so on. It's kind of fun, but also a little daunting. What are you getting yourself into? And I remember an Aleutian fisherman saying to me once, there are 2 modes when you're at sea in the Aleutians, boredom and terror. And oh boy, did we get some of both on this trip. So while we were out on the Steadfast, we were run over by a hurricane, a very rare, extratropical cyclone that ran right over us. And we actually retreated into another island and rode it out in a cove for a few days. It was rough, and it was frustrating because we were losing time. You can see weather hold. I think out of 20 days that we were at sea, we maybe managed to work 7 of them. I think I managed to work 5 of them. And you can see here, I don't know if you can tell, this is an improvised instrument that some joker on board came up with, our pukometer, little rock on a string. And we definitely, this thing pegged a few times, let me tell you. So terror, but also a lot of boredom. And so we had a lot of time and frustrating boredom, because you can actually see these are nice days. And what are you guys doing kayaking around and sunning yourself on the helipad? Why aren't you out working? Well, it was because the places we needed to get to were fogged in. So we'd be in this little pocket in the sun, and we couldn't fly because the weather was so changey, or the place we needed to get to was socked in, and we couldn't take that risk. So we entertained ourselves quite well. This is analog Wordle, lots of napping, lots of fishing. This is Alan and the biggest he won the trophy for the biggest halibut. This is me giving a science lecture. I think people were more excited to watch the fishing derby than that. So it was good times, but ultimately we did manage to get our work done. So you can see the weather conditions are marginal. Here's us doing a sling load by helicopter with the beautiful rainbow, but we were kind of having to really jump in and out and work very fast because we were getting these little weather windows. But in the end, here's my Top Gun moment. We got it all done, and here's our happy, smiley crew. It was incredible how efficient we got. And the key thing that I wanted to do on this expedition was I wanted to put seismometers out around all of the islands to basically do a CAT scan of this area. So the concept here is that we use the energy from earthquakes, whether they're kind of tectonic earthquakes in the subduction zone or distant earthquakes even, and we want to see what their energy does. So we might expect that if there's magma here, we would see the energy from this earthquake come in kind of slower than it should on average, and we might see it come in faster. So we'll be hopefully returning next summer to pull these instruments out. This is the big test right here. So we're very excited that we were able to do this. And these are, we were able to put out 6 seismometers that we have here at Carnegie. So these are really great systems. They're the Carnegie Quick Deploy box that Mike mentioned. We were able to develop them here and test them in a range of environments around the world with very generous support from the Brinson Foundation. I do have one of them up at the front, so I invite you after the Q&A if you'd like to come and see. It's a really clever system. It's kind of a seismometer in a box, and it helps us work really fast, and yet they run through the winter in these harsh environments. And then we were able to put out through the AVERT project additional seismometers. So we're very excited about getting this data back. But I want to finish on something incredible that we didn't expect in September 22. This was the goal. And we got out to several islands, and we got out to Cagamil. So Cagamil is a very special place. It is a very sacred land to the Unangim or Aleut people, and we were extremely privileged to have gotten permission from the Aleut Corporation to be able to work here. The Aleut consider this the birthplace of their people. It is a very sensitive area, and it was really remarkable to be able to work and to deploy. But when we got there, we found so much more. We found a giant lava flow. We'd sort of been staring at this thing from space, from the satellites and Google Earth and some other Landsat imagery. But we couldn't quite tell at the resolution. This is all one big lava flow. It all came out at the same time. It's probably been eroded back, but just on what we can see on land, this is 1 to 2 cubic kilometers. That's a lot of lava to come out of the ground all at once. And so we think this actually might be the source vent for this caldera. I mean, this is a huge piece of evidence, and we sampled it, but we also, got a better sense of its size, its minimum size. And just to put this into context for you, there are similar large lava flows at other caldera systems. So Newberry caldera is another very well-known caldera in Oregon. It has a very similar lava flow, very similar textures. It's an order of magnitude smaller than this one. The largest one of these flows on Earth, which is associated with a massive caldera in northern Chile, it's bigger, but this is a big lava flow. And this is only found in association with big calderas. So you have no idea, we were jumping up and down, but it got even better. We did the geochemistry. So remember again, the old crow, and we weren't able to match this infamous volcanoless deposit that so many scientists have worked over the years. It's a very important chronostratigraphic marker for all sorts of other fields, but it's also a big eruption that we're missing. So now I want you to look at the green. The green is the Cagamo lava flow. It's a dead ringer. This is probably something that oozed out right after this vent erupted the old crow. So we don't have an age date yet, and this is probably where the story is going to go completely wrong. I've been disappointed before, and this is also the most controversial thing that we've said. This is a very controversial thing among volcanologists who work on these deposits, and we could very well be wrong. But if we get an age date that matches the known age of the old crow, there it is. There it is. So the other thing we found was actually evidence for Cagamo being really active and recently active. We found large ash deposits on Cagamo, very local looking deposits. This thing has been making big eruptions recently. We found lots of thermal features. It's very hot. We found gases coming out of it that have a chemistry that suggests that there's active magma feeding them. So Cagamo is the center. Okay, so in summary on the caldera story, is IFM the site of a large volcanic caldera? Yes. I mean, I still could be wrong, but I'm going to say yes. To me, it's absolutely. And yes, this may be the source of the old crow. A 200 cubic kilometer eruption, a massive eruption. Is it potentially active? Well, we're still going to wait until we get our seismic data next year, and we'll do the tomography. But we've seen the gravity. We've seen that Cagamo is still active. It's hot. It's degassing. It's been erupting recently. But potentially active. Okay, is it going to have a big eruption? We actually don't think so. We see no evidence for that. What we actually think, and this is also by analogy to other volcanoes around the world that are very similar to Cleveland, basically that Cleveland, that kind of low-level continuously active thing, volcanoes like that sit on the rim of large calderas. So Sakurajima in Japan is a famous example. And what we think is actually that Cleveland's just going to keep Clevelanding as it does, And that's basically what happens after you have a large caldera. You kind of got a leak on the edge where the roof is caved in, and it's pretty easy for the magma to get out and decast, and it's just going to keep going, low-level eruptions. We don't really think this is going to be a place where there is a massive eruption, but we don't know. Okay, so I want to come back and finish the talk the way I started. I want to zoom back out and talk a little bit about the field of volcanology. And I want to start with an analogy to weather forecasting. So I'm talking about one volcano, and really, if you've noticed, I'm just talking about pattern recognition. I mean, there's no physical, we modeled the gravity, but we're really just kind of like, okay, well, we saw it at that volcano. So we're really still in kind of where weather forecasting was millennia ago. Red sky at night, sailor's delight, very regional. Just people living in the environment, recognizing patterns and using that to understand what the weather is going to do next. Weather forecasting then moved on to building instruments to actually make quantitative measurements, Da Vinci. We've done that. We're still trying to get them out. A lot of Earth's volcanoes have no instrumentation on them. But then that's spread to kind of, okay, let's take the instruments and have a consistent observation network. And then in the revolution of weather forecasting was in the 50s, where we actually started moving towards where we are now with physical models, computational fluid dynamics informed by large amounts of data that give us very quantitative forecasts. And so in volcanology, I think we're kind of around here. We're sort of a century and a half or so behind. And we're still just working to get instruments out, an observation network on all of the active volcanoes. We are starting to get some hints in volcanology, especially through machine learning. We're starting to get into computer models, but we're, again, really data limited. So, however, it's a really, I think we're right on the cusp of this transition. I think the next decade or two are just going to be incredible in volcanology. And I've been very excited and privileged to be involved in two major initiatives. One is called Subduction Zone in 4 Dimensions. I'm the vice chair of this initiative. It's a massive experiment. It will take decades. And one of its elements is we plan to instrument 50 volcanoes throughout Chile and North America for several decades to do a very systematic comparative study of their behavior and to tie in geochemistry and their eruptive history. So this is amazing. It's a huge experiment. We've been supported by NSF for to the tune of about 5 million so far in planning. That's the scale of these sorts of things. But it is moving forward, and I invite you to look at our website, sc40.org. Another initiative that I just very, very recently was invited to join its board of directors is called Volcano Aid. This is a startup nonprofit based in the UK that is more focused on advocacy and coordination, global coordination. So right now, each country does its own monitoring. So we have very different levels of instrumentation and protocols for warning and interpretation. And so really the aim here is to start talking globally about kind of a standard approach and normalizing the way things are done. So this is a very exciting, very new, it's just getting off the ground, seeking seed funding, hoping to launch next year, but the website is there if you'd like to take a look. And so on that point, you can clearly see I'm very excited. I can tell that you're all big fans of volcanoes because you gave up a beautiful fall evening to be here. So I just want to end with a promise. And the promise is that our understanding of these beautiful and terrifying systems, these volcanic systems that both enable and threaten the habitability of our planet, is on the cusp of a revolution. Thank you. Everybody's upvoting the question on the Puffin story.
That was fantastic. And we are going to have a Q&A now. I guess we're using these mics here.
Yep.
And we will start with you all here, and then we'll go to a few questions that are coming in online. I saw is that on? Yes, there you go.
It is hot. Yes, I was just wondering how seismometer design has changed over the years.
It's gotten a lot better. And actually a lot of that seismometer design has happened here at Carnegie. So Selwyn Sachs built some of the first broadbands, and they're tanks, I can't imagine. And now we've got these very robust systems that are the size of a coffee can. So it's just become a lot easier. We can put these things in backpacks and helicopters, and we can take them out. They're more power efficient, so they run for longer. They have less of a failure rate. They're very sensitive. We pick up a lot of smaller signals. And that's been really, really critical to our field. And really just in the past 10 years, I mean, the quality of our instrumentation has gotten so great. And we're very lucky at Carnegie to have sets of these next generation seismic instruments. So it's changed a lot, and we're actually pretty happy. We just want more, and we want them out everywhere.
I was just wondering if modern ones have any moving parts, like strain gauges instead of things that.
Yeah, no, there's actually a very clever mechanism that makes them work and that makes them sensitive to a broader range of frequencies than a mechanical system. It's called force feedback. So there are free elements, but they're basically held in place by electrical current, and we measure how much current it takes to keep them still, or voltage, excuse me. So there's something that could move, but the way the system works is it keeps it from moving, and it measures how much work it has to do to keep that little free piece still, rather than the old days where we actually had swinging or moving things inside generating the current.
Hi, when was the last really big eruption in the whole chain, and really of that particular, circle of islands? And how deep is the actual magma chamber there?
So the first question, in the chain, it depends on how far back you want to go, but the largest eruption of the 20th century was from a volcano or a set of volcanoes called Katmai in 1912. That was a big eruption. We don't think as big as what's happened in earlier times throughout the chain at IFM. But that was the largest eruption globally in 100 years. And so that's closer to Anchorage. It's where, if you watch the bears at Brooks Falls, it's where that is. And that's a big known caldera system. It actually formed a caldera during that eruption. The biggest eruption in the Aleutians ever, maybe the Old Crow, maybe at IFM. If we can tie that together, but yeah, Fisher has had a big one. There have been a few very large ones, but much, much older. The most recent one was the Katmai eruption, and that was a big one. Excuse me, part two, how deep? It's hard to say right now because we're really waiting on the tomography for that. But the gravity models kind of put it around 5 kilometers depth, which is really a typical depth that magmas like to hang out, especially in the Aleutians. So it's interesting that gravity anomaly, that model, which was still very, very rough. I mean, we'd like to go back and actually do a better gravity survey. It actually ballparks it at about 5 kilometers in the center, which is about the right spot for where we see magma ponding in many of these systems.
Yeah, go ahead.
You showed the pattern of eruption on the Cleveland string, and it was many more than everyone else. It looked like the interval in the eruptions, there was a pattern to it, or there was a symmetry. Is that an accident or something driving that?
Wouldn't surprise me. I don't know the answer off my head. I think this is, again, the type of thing that we're sort of moving towards, rather than just studying the individual eruptions and the individual volcanoes, trying to zoom out. And this is, the type of thing you might approach with machine learning or other data science tools of, is there actually a regular pattern there? But it also wouldn't surprise me. We know that volcanoes kind of wax and wane sometimes. So I think quite possibly, but it also could be that if we had a longer record, we might see that, no, it's just random, or that it does that sometimes, and it spreads out evenly some other times, and sometimes it's random. But yeah, it's the type of thing we'd like to know. And we know that on some level, volcanoes will go through phases of greater and less activity at an individual system.
So is there a significant change in either the wildlife that lives inside this ring or a temperature change of the water that's inside the ring?
I asked the crab fishermen that. And look, they would know, right? I mean, and I was, when we were waiting for weather to get out of Dutch Harbor, we had nothing to do but sit around and talk to the crab fishermen, who are actually very knowledgeable and interesting. And they felt like, no, I mean, there hasn't been anything changing there that they've noticed or that they've heard of over the longer term. The way to actually answer that would be to involve the biologists, maybe do some coring and look at, isotope proxies for temperature. That's something we would like to do. It's very difficult and expensive. But we just don't have any circumstantial or hard or, instrumental or quantitative evidence for that. But it would be an important question, particularly in understanding, is it the system kind of getting fed and increasing versus, is it dying down? And you'd probably want to approach that through kind of a geologic record, maybe put some drill cores out there, maybe someday.
I had a question about Amchitka, but first I just wanted to thank you for a fantastic presentation. And it seems like we're really on the brink of learning a lot. And, there's a lot we don't know that you presented very honestly. So I hope Carnegie can continue to support you as part of the team here for a long time.
He's not a plant.
Well, NSF, all of us. So it was hard to tell from your map, but certainly you presented evidence that the caldera could be, quite a bit larger, and that's to be determined. But a little further out there, and I don't know how much farther, it was hard from your map. We know that the United States detonated 2 of its largest nuclear warheads underground on Amchitka Island, Cannigan test 5 megatons and over, leaving in place all the nuclear materials from those tests. So what is the potential overlap of your caldera with all that nuclear material that we left there in 72, I guess? And, could like people are concerned about Idaho National Laboratory, where there's our plutonium disposal in the ground, where there's also volcanism.
Yeah, I think it's far enough away that that's not a concern. That's farther west, but it's enough distance away that I'm not a nuclear scientist, but I don't think, but we're aware of some of, there's still unexploded ordnance on some of these islands, and the scientists who work on many of these, especially the further to the west, have to kind of be a little more cautious about this. There was a large military installation on Okmok, the Roman Republic one, that's now a big cattle farm, but they're world-class cattle. I haven't eaten them, but apparently they're very high-end. And, they go through USDA testing and so on. And I've never heard anything about any, issues of contamination or anything. So I think that's maybe far enough away that it's not visibly affecting this part of the Aleutians. Maybe, that's what you're doing. Thank you. Yes, I think DOE funding would definitely let us say that really confidently. Thank you.
Okay, we'll take one more question from the audience, and I've got some online questions as well.
Hi, I really enjoyed this talk too, and thank you. Is there a chance that there's a magma conduit all the way along the Aleutian Islands, or is there a moving hotspot that created the Aleutian Islands? Could you go into that a little bit?
Yeah, I sort of skipped over that. So the Aleutians are a subduction zone. We know this pretty confidently. This is basically the Pacific plate diving underneath the North American plate. And at some depth, undergoing some chemical reactions of that hydrated oceanic crust, juicing the wedge of the mantle that's formed by that subduction. And that's really what's driving all of these volcanoes. It's an interesting question you raised, though, and one that I didn't have time to get into here. And one of the big questions that SC4D is actually aiming to address, okay, well, so they're all the same subduction zone. Why are they all so different? And why are there individual ones? Why do they pop up where they do? Why are the big ones only in certain places? We have some hypotheses. I didn't have time to get into that for this one, so if you want to see afterwards, but this is the type of thing that we're really trying to understand, and that we don't have a great answer for. There are some ideas about, wavelengths of diaparism in the mantle, but really trying to test those ideas and trying to understand why, if they're all in the same system, do we have such a range of characters and personalities? That's really what we're trying to do through SC4D.
Okay, last question.
In your conversation about the source of I think it was the Old Crow eruption, you had mentioned there was controversy over that. Why?
Yes.
I don't have any knowledge of this, but
Yeah.
you convinced me, so I was
Just, I didn't show you the trace
Good
elements
question.
because I thought that would be too much for a public talk. There's a little, so I showed you like the major elements that make up the magma, the silicon, the aluminum, but if you get into like the more sparse, the trace elements, those should match too. And there's some mismatches there between the Old Crow and the Cagamow flow. And one of the things that we're kind of arguing over, arguing in the scientific sense, is, this is a flow. It erupted under different conditions. It was more degassed, maybe a little time later, maybe as, a depleted of what the Old Crow magma was. Does that account for that mismatch, that more subtle mismatch that's in there? And so that is actually kind of, let's go back and look at the subtle differences in places where we know that this flow is related to this deposit. That's work that still needs to be done. And surprisingly, a lot of that trace element data don't exist where we can actually say, is this a reasonable difference for two things that are still, a match? So that's kind of what it comes down to. And then the age date will be the key thing. We should see that. We know that, well, actually the date of the Old Crow, not to get too far along, the date of the Old Crow is actually very hard to pin down. In fact, there was just a new paper a few months ago that shifted it again by a few tens of thousands of years. So age dating is very challenging in these types of rocks. And, hopefully a similar age date on the Cagamow flow will help say yes or no. But there are big error bars on all of these age dates and different groups that are very convinced that it's this age versus that age. But yeah, long, complicated answer.
Okay, we're going to take a few questions if you'll allow us, Diana.
Of course.
We've got a clear winner, but we're going to wait till last for that one.
Uh-oh.
The second most popular one is, in what scale did this caldera eruption compare to the recent Tonga South Pacific eruption?
It would have been bigger. We still don't have. So Tonga was another challenge. This is the Hunga Ha'api eruption that happened in January of 22, because I was getting on a plane in Chile then. It's underwater. It's very remote. The whole system is underwater. The eruption interacted with the ocean, so it's a little harder to just go and figure out what the volume there was. My sense is that it's smaller. In fact, I'm pretty sure, but I can't put numbers on that, but it would have been smaller than what we think happened at IFM during the cataclysmic. So there was a caldera formed. I think there was some bathymetry on the order of a few kilometers, but again, this was a place where there was a lot of interaction with seawater. And so the mechanics of the whole thing is a bit different, and we don't have as much of the deposit, which is normally we just kind of add the deposit together to figure out the volume. So we don't really have an estimate of the size, but I think smaller, significantly smaller. Hunga Tonga would be significantly smaller.
Next up is laser interferometry still used in volcanic geology to measure shifts between the land masses?
I haven't seen it done. So this is a technique that became really famous at Mount St. Helens. They hung a target on the cryptodome, the bulge, and they were basically figuring out by shining a laser and seeing how far. It's not really done that way anymore because we use GPS, but actually in the 2004 St. Helens, they were doing something more like photogrammetry of a similar, where they were kind of watching spots move around through repeat imaging. So not quite the same thing, but sometimes old school is the best way, and maybe a creative twist on it because we have better camera systems, high rate cameras, but I haven't seen the laser interferometry in a while. That's not to say somebody's not doing it. We have a tool bag and we use what works when it works.
So how do you manage the data so that everyone can access it?
Yes.
Very good question.
We in seismology are really fortunate to have a facility funded by the NSF. It's currently run by the EarthScope Corporation, the National Geophysical Facility. It was actually in part started here by Carnegie scientists, and it's a fantastic repository of raw seismic data. And if you are funded by NSF, or if you use instruments that belong to the national facility, you are required to contribute your data to share it. You get a 2-year moratorium embargo, but you are required to put your data in that system. But even then, many people, in fact, I put all of my data in there because, whether I have to or not, because it preserves it and it makes it accessible to other people. And I said we're data limited, but at the same time, in individual data sets, more eyes and more approaches are better. So I think it's partly that we have a really good system for sharing and a requirement, but also I think we have a culture after several decades in seismology, especially, we just have a culture of sharing data. And I think that's a fantastic thing.
And last but not least, we need the puffin story.
I'm gonna set that up. Okay, so in 2015, no, this was in 2016. I was the shipboard PI, so I was the lead scientist on board. We were on the RV Maritime Maid that year, and it came with all the responsibilities that you'd expect: decisions about prioritization of targets and any issues that came up, but also some weird responsibilities fell into my lap. So one morning, I woke up, I rolled out of bed, put my fleece and my hat on, and I kind of was trying to make my way to the galley for some coffee. And when I opened my stateroom door, everybody was freaking out because this little puffin had gotten its way into the bathroom and couldn't find its way out. So I was, as PI, elected to rescue it. And it's probably illegal. I'm sorry, Fish and Wildlife Service, but we did get him overboard. I don't know who had the worst time, me or the puffin. You can see our faces in the picture. But you just deal with things as they happen. I mean, this puffin, and guess what? Let's get a towel. And it was one of the cuter wildlife encounters I've had in the field, but we go into the field to study the rocks or put instruments and biologies in the way. I've had all sorts of critters in my instruments and so on. So it's part of the job. And it was my job, apparently, that time. So there's the puffin story. Yeah. Thank you. Yeah,
All right,
instead of
great.
helping, my postdoc was taking pictures. So he was a little upset. I was really upset, but we got him overboard and he seemed fine.
That's fantastic. Well, thank you so much,
you.
Diana, and thank all of you for coming. And I think if you want to come up and look at the seismometer, and maybe if you want to talk with Diana for a few minutes, that'd be fine. We'll see you next time.
Last slide for our.
The most dangerous volcano, or super volcano, or mountain in America now.
So
Because you have to say super volcano.
I know.
There's millions of calderas. That doesn't mean anything.
I put it in the title. I mean, it's
Yeah,
we're sort of on the fence.
I mean, there are only what, 10 or 11 super
Real
volcanoes,
super
and half of them are American.
So